Okay, good. Okay, so thank you. Thanks a lot, Abdulrahman and Yasin and so on for the setting up. Yes, so welcome to the course on optimization for data science. My name is Hamza Fawzi. I'll be giving this course. So first, just some kind of admin stuff. I mean, the details of the course. So this is a 4-day course this week. So I mean, this Monday until this Thursday, we'll have 2 sessions per day. So one in the morning, so from 10 to 11:30, and one in the afternoon from 2 to 3:30. So this is Morocco time. And the topic of the course will be optimization algorithms used in data science. Okay. So kind of, I'll start the course by a bit of motivation, some examples of optimization problems that we see in data science, some of their characteristics. And then after that, I'll go into the kind of the more technical details of the course, the core of the course, essentially. Okay. So, okay, so I'll start with something, I mean, probably the basic question in data science and in statistics, we can say is the task of linear regression. And the problem in linear regression is the problem of learning a certain linear prediction rule from a set of predictors X to a certain response variable Y. Okay, so we have some predictor variables X1 up to XP, so P is the number of predictors, and we're trying to estimate a certain response variable Y as a linear combination of these predictor variables. Okay, so we want to have Y approximately equal to W1x1 plus W2x2 plus WPxP. And I write this in shorthand as W transpose X, where W is the vector of weights, W1 up to WP, and X is the vector of predictors, X1 up to XP. So some examples of questions like this, I mean, such questions are I mean, everywhere in science and engineering, but let me give you some concrete examples. So let's say that you want to try to predict the risk of diabetes or say life expectancy, okay, as a linear combination of some health characteristics, that some things that you can measure, something like the blood pressure, the glucose level, I mean, if you smoke or not, cigarettes, and so on. Okay, so you have a certain vector of predictors, and you're trying to find a linear combination of these components that will predict the response variable that you're interested in. Okay, another example could be that you have a certain image, and so an image, you can represent it as a very long vector where each component of this vector gives you the intensity of a pixel. Okay, and the response Y that you would like to know is something semantic information about the image. For example, which digit, I mean, if these are images of digits 1, 2 up to 9, let's say, you want to know which digit is represented in this image, or you want to know, does this image contain a car? Does this image contain an airplane? Does this image contain a book? And so on and so forth. Okay, so you're trying to learn a certain function Y. Y is f of x, and in this case, I'm looking just for a linear function of x. Okay. So these are just 2 examples. There are obviously many other examples in biology, in gene expression data, in system identification. If you have a certain black box that you can kind of trigger using certain inputs, and you're trying to learn what are the inner mechanisms of this system. So kind of the simplest approach to study such a problem is to do least squares. So what we're given here, how do we do least squares? So we assume we're given some labeled examples. So someone already gave us labeled examples. So we have certain vectors xi and the associated predictor, the associated output yi. So this could be, let's say, the blood pressure and this glucose level and so on, associated to their life expectancy. So these are patients that we already, I mean, these are people that we already know. And then we're trying to predict from these training examples a certain, I mean, we're trying to learn these weights functions, these weights, these weight variables from these labeled examples. Okay, and so as I said, the simplest approach is just to do what we call least squares. So you're trying to find the vector W that will minimize the overall error on the labeled examples. And so here we measure the error as the sum of squares of the error. So the sum of squares of the deviation from yi, which is the true response variable for example I, minus w transpose xi. Okay, and w here is the variable that I'm trying to learn. Okay, and so I can write this in a simple, kind of a more compact notation as norm of y minus xw squared, where I've collected all the response variables in a vector y, y1, y2 up to yn, and all the predictor vectors in a certain matrix big X. Okay, so linear regression is something that is very old. I mean, it dates back to Gauss. And we have very good, in fact, this problem has been extremely well studied. In fact, the solution of such an optimization problem is equivalent to solving a linear system. This is the linear system called the normal equations. Okay, if you differentiate, this is because the gradient of this function is just a linear function, which is given here. And so solving, I mean, we have very good ways to solve such a question. Okay, but in many cases, especially in modern data science applications, least squares is not can be unsatisfactory, especially in a certain regime when p is bigger than n. So this is a regime when we have many more predictors than samples. Okay, so this is something that happens a lot, for example, in biology, where the predictors are, for example, gene expression data. So you have, for each gene, you have a certain expression level of this gene. So you have many genes, and you're trying to predict a certain variable y, and the number of samples n can be much less than this number of genes. Okay, so this is because each sample corresponds to a certain experiment that you do, and so on. So you could have many more genes than samples, than n, than training, the size of the training set. And so in this case, actually, this problem is ill-posed because you have you have many possible solutions. And in fact, in such a setting, something that you would like to do is to try to identify which genes are actually important. Okay, so what you would like to do is to find a certain w, a solution of this optimization problem. Okay, so a w that is sparse, so something that contains many zeros, and such that y is approximately equal to xw. Okay, so you want to be able to predict the response variable y as a linear combination of the predictors x, while at the same time ensuring that the vector w is sparse. This is very useful in terms of interpretability, because if you this means, I mean, if w is sparse, then this means that only I mean, whenever you have a component I of the vector w that is 0, wi is equal to 0, this means that actually this predictor is unimportant to predict the response variable y. Okay, so if you have a vector w that is sparse, this essentially allows you to say which predictor variables are actually important and which ones are not important. So for example, which genes are important in predicting the response y and which genes are unimportant. So this is something that is very useful from the interpretability point of view. Okay, and so in order to do this, what people have proposed is they have proposed something called the lasso. So this is something that is mostly studied in statistics, where you still have this least squares objective function. So you want to again minimize the data fidelity. I mean, you want to minimize the how far you are from the data, from the training set. But you also want to penalize a certain a vector w that has a large L1 norm. So here L1 norm is a term, is what we call a regularization term that promotes sparsity of w. So people have observed empirically, but they have also proved this theoretically, that imposing such a regularization term, so a linear, lambda times the L1 norm of w, this tends to promote a sparsity of w. So the solution of such an optimization problem usually will have many zeros, unlike what you will get if you just apply the least squares norm of y minus xw squared. Okay, so in order to illustrate this, I've done a simple, I have a simple Matlab script that I can share with you to kind of explain this. So let me try to do this now via Zoom. So let's see. This is, so if I new share and I do, let's see what happens here. So actually, let me just share my desktop. That would be easier to share. Okay, so you can see. I hope you can see here my MATLAB. Yes, I think. So you can see my MATLAB screen. So I'm kind of generating a simple example. So I have the number of predictors I have is 1,000. So I have many predictors, and the number of observations is 500. So this is smaller, as I said, than the number of predictors. Okay, and I generate, in this case, I'm just generating some synthetic data just to try out. So, okay, so I'm generating a certain, this is the vector of predictors, X. This is the kind of the ground truth, which in this case I have is mostly zeros except the first 100 components. Okay, and the vector Y is X times W plus some error E. Okay, so this is kind of the noise that you could have in an experiment. And then, okay, so then I compute the least square. So in MATLAB, this is just X backslash Y. This is very simple. Again, this is solving just the linear system, the normal equations. And then now I invoke an optimization package that will solve this lasso problem, which will essentially minimize the sum of squares of the errors plus lambda times the L1 norm of W. Okay, so I will call this. This will run a certain algorithm, so which I will not explain, which is essentially this. You will, I mean, at the end of the course, you will understand essentially what happens behind the scenes. Okay, and now let me plot the solution. Okay, so this is what you can see. So this is the ground truth. So this is this is the vector W, each I here. So this is essentially telling us that the first 100 components of W are non-zero. And then everything after so components from 100 to 1,000 is equal to 0. So if you do just least squares, what you get is something that is kind of not sparse at all, okay, very far from the ground truth. But if you do regularization with the L1 term, you see that you can essentially recover the sparsity pattern of W, and you can see that all the components from 100 to 1,000 are zero, essentially. So you can recover essentially which genes, in this case, which genes are actually important. Okay. So so this is one example of an optimization problem that is used a lot in data science. So whereas the problem, this least squares problem is considered quite easy to solve. I mean, it's just solving a linear system. This problem is, I would say, more challenging. One reason why it's more challenging, for example, is that the regularization term that you see here is a non-smooth term. Okay, the L1 norm, this is the sum of the absolute values of Wi. This is a non-smooth function. It is a convex function, but still it is not smooth. So for example, you cannot apply a gradient method to this problem because the L1 norm is not smooth, so it does not have a gradient in general. Okay, so this is, again, this is just to give you some motivations. One problem used in data science a lot, and so we'll see throughout the course some techniques to deal with non-smooth optimization problems. Okay, and we'll look at one of the most famous algorithms used to solve such lasso problems. Okay, so this is the first example that I wanted to explain. So let me now move to another type of optimization problem. So okay, maybe not in data science exactly, but related to AI and more particularly in robotics, something that is a problem in robotics. So the problem of optimal control, or more precisely, model predictive control. So here, what you have, I mean, it's a different setting. So you have a certain dynamical system that evolves according to, I mean, either a differential equation or a discrete time kind of equation. So the state xt plus 1 of your system is a function of the current state xt and a certain input ut that you can apply. Okay, so think, for example, of an autonomous car. So you're trying to kind of control an autonomous car. So this autonomous car is a physical system. It has a certain equations of motion you can write. Okay, and the control, what you have to control is essentially in an autonomous car is the acceleration, if you want, and the steering. Okay, so you can control the acceleration and the steering, and what you would like to do is your car to follow a certain path. Okay, so so what you do essentially in such a problem is that you write a certain optimization problem. So you remember what you're looking for is the controls ut. So in the case of the car, that's the acceleration and the steering. And you want to minimize, I mean, in this case, if you're trying to follow a certain reference trajectory, you're trying to minimize the deviation from this reference trajectory, plus possibly a certain term that penalizes the magnitude of the control inputs, okay? Because applying high control inputs means spending energy, so you want to minimize also the energy that you're using, subject to obviously the dynamics of the system, and subject to certain hard constraints on the inputs u. For example, the acceleration that you apply in a car cannot be more than something. Okay, and this is a hard constraint, so this you have to put in the constraints. As well as the steering, you cannot steer more than a certain magnitude, and so you have to put this as a hard constraint in your optimization problem. So in the context, I mean, if we talk about robotics and so on, if we see how these optimization problems are used in practice, one very common usage of these optimal control problem is in a receding horizon control framework, or in a model predictive, what we call model predictive control as well. Is that essentially this problem is solved repeatedly at each time step, each discretization type step. So let's say, so for example, this optimization problem is solved, let's say 10 times at every second, and with a certain horizon t that could be, let's say, 10 steps ahead or 20 steps ahead. Okay, and you apply in this model predictive control framework, you only apply the first input, and then you go to the next step, and then you resolve the problem in the next state, in the next time step. The reason we do this is that because we do not want to stay in open loop for very long. Okay, because staying in open loop for very long means that you actually lose track of what is happening in reality. And so that's why if you want to be, I mean, you want to be robust to what's happening in reality and not relying completely on the model. So that's why you have to resolve this very often. Okay. And so what this means, if you want to resolve this at each sampling step, or each maybe 2 sampling steps, then you have very stringent running time requirements on the solution of such a problem. Okay, so when you I mean, such problems are solved in embedded systems, on cars and so on, and you need to have guarantees that you will find a solution of such a problem within, let's say, within 0.1 second or 0.5 seconds at most. Okay, so you have to be able to solve such problems with guaranteed running time. Okay, and this is kind of yes, and so this is kind of a constraint that one has to keep in mind when designing an algorithm for solving such a problem. Okay. Okay, so this was the second example from a different area. Let me now talk about a third example. So which is the problem of what we call community detection. Okay, which is a problem that is very natural in when you think about data sets, Facebook or Twitter and so on. So the idea is you have a certain graph. So think about a Facebook graph where you have nodes are people and you have links if those people are friends, for example. And what you would like to do is to identify in this graph two communities where essentially two communities. So this could be, for example, two people belonging to two different political parties and or something like that. And how do we define a community? We define a community as a set of nodes such that the connections within the same community is much greater than the connections across different communities. Okay. And another requirement typically that we would like to have when clustering a graph into two communities is that the size of the two communities are the same, are roughly the same, not exactly equal, but are roughly are of comparable size. So this is here. This is one graph that you can see. I don't know, maybe it has 600 nodes or so. So it's very difficult to see any two communities in this graph. So the goal of community detection is to try to identify, to try to label each node as being belonging to community A or to community B. So in this example of a graph, for example, this is an assignment of nodes to communities. Okay, and if I disentangle these nodes, this indeed satisfies the requirements that I said, because you can see that connections within between blue dots is much greater than connections between blue and red dots. Okay, so there are much more connections within blue or within red than across blue and red dots. Okay. So how do we solve such a problem? So I will explain to you one approach that people have proposed, and which is a very successful approach to solving such a problem. Which is based on an optimization formulation. So the idea is to define something like the adjacency matrix of a graph, but a signed adjacency matrix. So you define Bij to be the matrix. So it's an n by n matrix if you have n nodes in your graph. And so you put +1 if the nodes I and j are connected, and you put -1 otherwise if they are not connected. Okay, and what you do essentially now is that you, in order to recover these communities, what you do is that you maximize over all symmetric matrices X. Okay, so Xij is equal to Xji. You maximize the sum of Bij Xij. Okay, if you want, that's the trace inner product of B and X. Subject to now X is positive semi-definite, so X is a symmetric matrix, and X positive semi-definite means that all the eigenvalues of X are non-negative. And you require that the diagonal of X is equal to 1. Okay, so this sounds very kind of weird, maybe it's not. So I will not explain actually exactly where this is coming from. I'll just try to give some intuition of where this is coming from. The more kind of detailed explanation of where this is coming from is a bit more complicated. Maybe I will talk about it at the end of the course, but if we have time. But essentially what you want to do is to interpret Xij, which is a number. So you can show that if X is positive semi-definite and the diagonal is equal to 1, then each entry of Xi of X has to be between -1 and 1. So we can interpret Xij between -1 and 1 as a likelihood that nodes I and j are in the same community. So likelihood, so here this is between quotes because Xij is equal to +1. This is very likely that I and j are in the same community. And -1, it's very likely they are not in the same community. Okay, so obviously I and I are in the same community, it's the same node, so this has to be equal to +1. And otherwise, once you solve this, and then you look at the Xij entry and you look at its sign, and this tells you whether it's more likely I and j are in the same community or they are not. Okay. So again, I have a simple Matlab experiment. I hope it will work. I can show you. So let me just clear the thing. Okay. So what I'm going to do now is I'm going to generate a certain graph with 200 nodes. Okay, and I've set a certain P and Q. So P here is the probability of having a connection within the same community, and Q is the probability of having a connection across different communities. So you can see I've set P that is much larger than Q. Okay, so let's generate a graph here. This is the matrix B. What I've put here, what you've seen here is the matrix B that is on the slide. So you can see, I mean, here the two communities, the first community is nodes 1 up to 100, and the second community is nodes 100 up to 200. And so you can see that there are nodes. I mean, whenever you have a yellow, this means that you have an edge between two nodes. So you can see that the edges between things in the same community, between nodes in the same community, is much greater than edges across communities. So obviously, if you see this, if someone gives you this plot, then it's very easy to see what the two communities are. But this is because kind of the nodes are arranged in a certain way that we can see it very well visually. But what the computer will actually see, here what I've done is that I've just permuted the rows and columns of this matrix. And now it's much harder to actually see two different communities in this graph. Whereas it's exactly, this graph is exactly the same graph as this one. Okay, I've just permuted, I've just relabeled the nodes in this graph. Okay, so now let me close these. Now this is the optimization problem I told you about, the one highlighted in yellow. The variable here is a symmetric matrix, an n by n symmetric matrix. What I want to do is to maximize the trace of b times x, subject to x is positive semi-definite, and subject to the diagonal of x is equal to 1. Okay, again, I use this package called CVX to solve this problem. So let me just run this cell here. Okay, so now it is solving this problem. Okay, and now what I can do is I can look at the solution. Okay. Okay, and this is what I've done here is I've looked at this is the matrix X, but I've plotted just the sign of Xij. Okay, so you can see here that so up to some kind of mistakes, but overall we see that this method has detected that there are two communities. Essentially, the first community is this one, okay, and the second community is this one. Okay, so the second part. So essentially, it has recovered that the first community is nodes 1 to 100, and the second community is nodes 101 to 200. Okay. So okay. So this was just to give you some examples of optimization problems. So let's kind of go back at the three and have a look at the three optimization problems I mentioned. So this one, you can see it's weighted. So it's a combination of, you have a least squares term and a non-smooth term that promotes sparsity. Okay, this is an unconstrained problem. One of the difficulties of solving this problem is the non-smoothness of the objective function. The second optimization problem I talked about, now this is a constrained problem. So you have certain hard constraints that have to be satisfied. Okay, and again, you have some requirements on the running time, as I said, of in solving this optimization problem. Okay, here you can see that the objective function, on the other hand, is smooth. So this is another type of difficulty compared to the first optimization problem. So here you have constraints. The other one we did not have constraints. The third optimization problem, the objective function is a very simple function. It's a linear function. The difficulty, one of the main difficulties in solving this problem is this constraint here, is in imposing that the matrix X has non-negative eigenvalues. Okay, this is a convex constraint, but it's a difficult convex constraint to deal with. And so that's why solving such an optimization problem currently, this is an active area of research to try to find algorithms that can solve this problem for large values of n. Okay, so I've solved it for n is equal to 200 on my desktop computer here. But if I were to run this code with n is equal to 1000, which is a very typical graph size if we talk about social media and so on, then that would take much longer. Okay, so it is an active area of research to deal with such optimization problems. So in the last part of the course, I will talk about optimization problems involving such a positive semi-definite constraint, what we call a positive semi-definite constraint, that a symmetric matrix has non-negative eigenvalues. We will try to explain the algorithms that is running in this solver that I ran here, CVX. Okay. And probably I will touch a bit on what the current methods are to try to scale this up to to larger dimensions. Okay, so that is so this is just to give you some motivation of problems that show up in practice. This is obviously this is just a very small subset. I mean, it's kind of if you want an appetizer, just of to give you to tell you a bit about problems in data science. There are obviously much more problems. So now this is a very rough course structure about what are the topics that we will cover. So today I've done a small presentation, a small introduction about optimization problems in data science. The rest of the day will be devoted to some preliminaries in convex analysis. Okay, I will recall some of the basic notions about what's a convex function, what's a strongly convex function, smoothness, and so on, and we'll apply some of these notions to analyze the gradient method, probably the simplest possible algorithm for optimization, the gradient method. So we'll analyze its convergence and try to see what are the key properties that govern its convergence. Then tomorrow I will talk about some more advanced topics related to smooth optimization. We'll talk about general methods, I mean, how to incorporate what we call momentum in gradient methods in order to make it to accelerate the convergence rate. And in particular, we look at a certain example of gradient method with momentum, which is the Nesterov's fast gradient method. I will also, tomorrow, I will also talk a bit about duality, Lagrangian duality, and so on, and how duality can be used in the design of algorithms, not just as an analysis tool, but how it can be, how sometimes solving the dual is more advantageous than solving the primal problem. Then on Wednesday, I will talk about non-smooth optimization. We'll talk about the subgradient method, something called the proximal gradient method, which is usually the method of choice now to solve these lasso problems I talked about. And then on the last day, I will talk about some more advanced algorithms called interior point methods and path following methods. And these are usually applied to structural problems. So things like linear programming, quadratic programming, and semi-definite programming. These are algorithms that allow you to reach good accuracy. So these are algorithms that are typically used when you have constraints and when you want to solve your problem to high accuracy. These are the algorithms that we use, and these are the algorithms that is implemented, for example, in CVX. This MATLAB code that I ran is based on a solver that is essentially an implementation of path following interior point methods. Okay, semi-definite programming is a class of optimization problems involving semi-definite constraints where you have a symmetric matrix that you want its eigenvalues to be non-negative. And a typical example is this community detection example I just showed. Okay. And this is what I will do, what I will try to explain on Thursday, how, I mean, a high level, again, overview of how these algorithms work, how they work and what is their convergence rate. Okay, so this is kind of, this is all for the introduction. So now I guess I can move to the preliminaries. So now I'll move into more, the more mathematical aspect of this course. We'll look at the details. So what I will do now is I will switch now to my iPad. So please bear with me just 2 or 3 minutes before I kind of switch to my tablet. So, okay, I'll stop share this. And let me try. Yes, so let me try to share screen. Okay, so how do I do this? So Abdul Rahman, are you here? Or?
Yes, I can hear you.
Okay, so if I click on start broadcast, can you see? Okay, so you can see my iPad, I guess, now.
Yes. Yeah, you are sharing the screen.
Now, can you see this?
Yeah, convex sets.
Yes, okay, very good. Okay, so let me now work on this now. Okay, so let's see. Yes. Yes, so now let's go on to the more the more mathematical part of this course. So one, I'll recall some definitions. So the first definition I need to recall is what's a convex set. So I said that a set C is convex if so C is a subset of R in Rn. Okay, so if X and Y are in C and lambda is in 0, 1, then the convex combination lambda X plus 1 minus lambda Y is also in C. Okay, so a typical example of convex set. So can you see this? Yes. Okay. So this is what you want really. So is that if I have any 2 points X and Y in C, and I take a convex combination, so I take the line segment between X and Y, I want this to lie also in C. Okay, so that's a convex set. Okay, and an example of something that is not convex is something that looks like this, because if I take X and Y in here, and I look at the line segment between X and Y, this goes outside of C. Okay, so this is not convex. Okay. So now, what are some simple examples of convex sets that we deal with all the time are the first one is half spaces. So what's a half space? So a half space is you all know what's a hyperplane. So a hyperplane is something defined using a single linear equation, A transpose X is equal to B. Okay, a half space is just something where you just take one side of this hyperplane, and there is here this is the normal vector to the hyperplane. This is essentially half spaces are the main building block of convex sets. So you can show that any convex set is essentially an intersection of half spaces, possibly infinitely many. So here a norm ball is just it could be, this is the set of X such that the L2 norm of X is less than 1. Okay, this is a convex set, obviously, but it could be, let's say, the set of X such that the infinity norm of X is less than 1. Okay, in this case, that's just a square. That's also a convex set. Okay, and essentially, if you for any norm, the one ball is going to be a convex set. So, and this follows essentially from the triangle inequality of the norm. Now, a very important property is that if C1 and C2 are convex, then their intersection is convex. So, for example, if I take this is C1 and this is C2, okay, then the intersection of C1 and C2 is a convex set. Okay, this is a very useful operation geometrically. For example, if I take two half spaces, okay, so if I this is a half space, and if I take another half space, okay, then their intersection, which is here like this, okay, this is a convex set. Okay, and this is exactly, if you intersect m different half spaces, what you get is what we call a polyhedron. So if you intersect, if you have, this is a hyperplane, this is another hyperplane, and so on, and you intersect these guys, you intersect all these half spaces, what you get is something called a polyhedron. Okay, this is a polyhedron. And that's a convex set, and that is that's the convex set of that we typically see in linear programming. Okay, so so this is concerning convex sets. So let's now move to convex functions. So a function is convex if its domain is convex C, and if for all x and y in C and all lambda between 0 and 1, f applied to the convex combination of x and y is less than the convex combination of the values of f. Okay, so again, what this means is I have, this is my graph f, okay, and if I take 2 points, so this is f of x and this is f of y, okay, what you want is the line segment joining these 2 points has to be above above the curve. Okay, so this is convex. Okay, and a function that looks like this is not convex. Okay, because for example, if you take this point x and this point y, and you do the line segment between the two, this will be below the curve. Okay, there is you can move between convex functions and convex set through this concept of epigraph. Okay, so this is the epigraph. So the epigraph is essentially everything above a convex, above a function. So if you draw its graph, so if this is my graph, if this is my function f, then the epigraph is essentially this set here. Okay, so it is the set of t such that t is bigger than f of x. So it's the set of xt such that t is bigger than f of x. And so it is very easy to see that f is convex. Okay, so f is convex if and only if its epigraph is a convex set. So for example, here, the epigraph of this function, which is not convex, it is clearly not a convex function, okay? Not a convex set. Sorry, because again, you can there are 2 points you can choose, so that by drawing the line segment between the two, you will go outside the set. Okay. So okay. So yeah. So what are some examples of convex functions? So obviously, a linear function is a convex function. So f of x is equal to a transpose x plus b. That's a convex function. Okay, this is very easy to check. Okay, f of x is equal to the norm of x. Okay, this is convex. Okay, and here the norm, this can be any norm. And again, the convexity follows from the triangle inequality of the norm. There is a very useful property when proving convexity of a function, and that is the pointwise maximum. Okay, so the pointwise maximum of convex functions is convex. So what this means, i.e., So if Fi is a family of convex functions, then the function f of x, which is the max over all I in I of Fi of x, is convex. Okay. Again, proving this statement is again very easy, so I won't do it. There is a direct connection with the notion of intersection of convex sets, because you can show that the epigraph of this pointwise maximum is the intersection of the epigraph of the Fi's. So let me tell you why. I mean, this is a very simple observation, but it is a very useful one. So let me show you one application. So application. So if A so is a symmetric matrix, its largest eigenvalue is given by is lambda max of A. It is the max over all x that have unit L2 norm of x transpose AX. Okay, this is something that you have seen in linear algebra. The largest eigenvalue of a symmetric matrix is given in this way, x transpose AX. Okay. So now the key, what I want to explain here is that this guy, so this is linear in A for a fixed x. Okay, so if you fix x and you think about this, about x transpose x as a function of A, this is a linear function because x transpose A plus bx is x transpose x plus x transpose bx. Okay, so this is linear in A. And so now I have my, what I've written here is that lambda max of A is a pointwise maximum of an infinite number of linear functions. Okay, so this implies that lambda max is a convex function in A. Okay, so this means that lambda max of a convex combination of two matrices is less than the convex combination of the lambda maxes. Okay, this is an important application. The fact that the largest eigenvalue of a symmetric matrix is convex. This is an important thing to know. Okay, so this is so these are some examples of convex functions. We'll see more as we go along. Okay, and so a convex optimization problem is just the problem of minimizing a certain function f of x that is convex, subject to some constraint that x has to live in C, and C has to be a convex set. This is what is usually called a convex optimization problem. So this is given in an abstract form. Okay, typically, okay, C is given as some intersection of convex inequalities. So typically, what we have is that C is the set of X in Rn such that some Gi of X is less than 0, where Gi are convex functions. Okay, so Gi is given in terms of a set of inequalities, and each inequality is given by a convex function. This describes a convex set. Okay, but here what is highlighted in blue here is the kind of the geometric way. So I just want that my set C is a convex set, and yeah, so that's the general definition of a convex optimization problem. Okay, so so now before I go further, I need to recall a bit of definitions from analysis. Okay, the notion of a gradient and the notion of a Hessian, essentially. Okay, so I will now introduce these notions. So now if a function f is continuously differentiable, then this means that I can write its Taylor expansion around any point x in the interior of its domain. So I can write f of x plus h, where h is a small perturbation, as f of x plus the inner product of the gradient of f of x with h, plus something that is big O of norm of h squared. And here, the gradient of f is the vector of partial derivatives. Okay. Yes, okay, so I guess that's the only thing I need. So here, essentially, really what you're doing is you're just doing, so you have a certain function. I mean, this doesn't have to be a convex function. You're doing a first order Taylor approximation of your function. Okay, so this is your function f, and this is your Taylor approximation. Now, a convex function can be recognized by the fact that the function has to be always above its Taylor approximation. Okay, so if I draw a convex function, okay, and I draw its Taylor approximation. Okay, so this is you can see. So this is really just f of x plus the gradient of f of x y minus x. This is as a function of y, and this is really, if you can see, this is really f of y here. Okay, so you can see that f is always above its Taylor approximation, and this is true if you take the Taylor approximation anywhere. Okay, for any base point x, okay, you have it is above, the curve is above the linear approximation. Now, a very simple consequence, but an important one, is that if you have a point and the gradient is equal to 0, then x is a global minimum of the function. So it is important to note here that, maybe let me emphasize this point, is that whereas the gradient is something that is a local property of a function, so it only depends on the neighborhood of x, so the gradient of f at x. This inequality is something that is global. It tells you that for any h, for any x and for any h, f of x plus h is going to be bigger than f of x plus the gradient of f of x transpose h. So you have something, the right-hand side that you see here, f of x and the gradient of f of x only depends on local information of the function at x, but the consequence that we have is something that is global. Okay, and this is what makes convex functions very powerful. I mean, because you're essentially able to deduce global information about the function from just local information. So, and this is one such example, is that if the gradient of f of x is equal to 0, then x has to be a global minimum. Okay, and the proof is very simple, because f of y, if I just plug h is equal to y minus x, okay, f of y is bigger than f of x plus the gradient of f of x transpose y minus x. Okay, but this is equal to 0. Okay, and so what I have shown is that for all y, f of y is bigger than f of x. So this means that really the minimum of the function f is attained at x. So x is a global minimum. Okay, so so this is a key property. What is highlighted in yellow here, this is really a key property of convex functions. So now, very often, I mean, when we deal with convex functions, we will sometimes need a little bit more, we will need something called strong convexity, which is a strengthening of this inequality that we see here. Okay, and strong convexity essentially tells you that f of x plus h is not only bigger than f of x plus the gradient of f of x transpose h, but you also have a certain quadratic term here that a certain quadratic term here in h. Okay, so what this means is if I have my function, so I have my function here, that's f, okay, and I have my linear approximation, okay. This is what you get by just having the first two terms. But if I look at all three terms, what you get is the linear plus something quadratic, so you get actually a quadratic lower bound. Okay, so this tells you that there is a quadratic lower bound to my function f. Okay, so this is important. This is f here. And the Taylor approximation just gives you a linear lower bound. A strong convexity gives you something more, gives you a quadratic lower bound. And this is something that we will use sometimes in the analysis of algorithms. And the constant mu here is the strong convexity constant. So obviously any convex function is zero strongly convex, but often we'll be interested in strongly convex function where mu is strictly positive. Okay, and the behavior of the algorithm will often depend on how strongly convex you are. Okay, so this is one notion of strong convexity that we will use. There is another notion, something called L smoothness. Okay, and this is kind of the other side. So now we have a lower bound on the function f as a quadratic function. L smoothness essentially gives you an upper bound on f as a quadratic function. So note this inequality here. So so what L smoothness mean is that you have so let's see what can do. Okay, so you have a function. Okay, so recall we have so I have the linear approximation. Now L smoothness, what it will tell me is that I have an upper bound on my function as a quadratic. Okay, so this is a quadratic upper bound, and okay, let me maybe try to use a stronger. So this is my function f, okay, and what is in green here, this guy, this is what you see. Okay, this is a quadratic upper bound. Quadratic upper bound on f. Okay, this is what you get from L smoothness, and in fact, this is equivalent to. I mean, I will leave this as an exercise for you. Is that so f is L smooth? So f is L smooth. I mean, this condition, this quadratic upper bound, if and only if, essentially the gradient of f is L Lipschitz. Okay, so meaning that the gradient of f at x minus the gradient of f at y measured in the 2 norm is less than L times the norm of x minus 1. Okay, I will not prove this. This is something that is pretty standard. You can try it yourself, or you'll be able to find it easily in textbooks on optimization or on convex analysis. Okay, so so kind of to summarize now, just strong convexity and smoothness. So if f, oops, what's happening here? So f is mu strongly convex and L smooth. Okay, then I can sandwich f between two quadratic functions. Okay, so I can write f of x. On the one hand, I can write this as f of x plus the gradient of f of x transpose. Sorry, so I can write this. Let me write f of y. This is less than the f of x plus gradient f of x transpose y minus x plus L over 2 norm of y minus x squared. Okay, but I can also lower bound my function as f of x plus gradient f of x transpose y minus x plus mu over 2 norm of y minus x squared. Okay, so this is really, so again, I want to use two colors here. So this is L smoothness. Okay, and I don't know. So, and this is mu strongly convex. Okay, so essentially I'm sandwiching f between two quadratic functions, and let me draw a curve. So let's assume my function is like this. Again, it's always so let me draw in red. I have a quadratic upper bound, a quadratic lower bound. Sorry. So, this is follows from strong convexity, and what I have here. Sorry, this is a bit difficult to draw, but okay, so I have another. I have a quadratic upper bound on my function. Okay, and just to make sure, this is my function. This is my function f. Okay, it is upper bounded by a quadratic function, and it is lower bounded by a quadratic function. Okay, this is really what you have to keep in mind when talking. I mean, when you think about L smoothness and mu strong convexity. This is okay. So some functions are not mu strongly convex. For example, linear functions are not strongly convex. But some functions are, and we'll see this has an important implication for the convergence of something like the gradient method, as we will see this afternoon. Okay. Okay. So this is it. So kind of to finish this this section on preliminaries, I want to talk about second derivatives because this will be very important. So now, if f is twice continuously differentiable, then I can do a Taylor expansion of f to the second order. Okay, so the gradient was the information I need for the first order. Now the Hessian is what I need for the second order. So this is the Hessian. And the Hessian is a matrix. It's actually a symmetric matrix. So this. Okay, that has the second derivatives of f with respect to different directions. Okay, so the ij entry of the Hessian is d2f over dxi dxj. Okay, you can show that this is a symmetric matrix when f is C2. And the quadratic term that we have here in the Taylor expansion is H transpose the Hessian of f of x times H. Okay. So yes, okay. So I mean, if I expand this term, so maybe just to be completely explicit, if I expand this term, this is just the sum over all ij of hi hj, okay, times the Hessian times ij, okay? So obviously, if you're in one dimension, that's just h squared times times the second derivative of f. But this is for multivariate functions, which is something that obviously we will study. Mm-hmm. Okay, so now Hessians are very important to think about when talking about convex functions, because a function f is convex if and only if the eigenvalues of the Hessian are non-negative. Okay, so again, remember that the Hessian is a symmetric matrix, so all its eigenvalues are real. And so if the eigenvalues are all non-negative for all x, then the function f is convex. And this is an if and only if your function is C2. And there is also a very nice characterization of mu strong convexity and L smoothness in terms of the Hessian of f. So the function is mu strongly convex if and only if the eigenvalues of the Hessian are all bigger than mu. And mu here is a strictly positive number. Okay, so again, it's kind of something, as the name suggests, it's something stronger than convexity. So you want not only that the eigenvalues are non-negative, but the eigenvalues are strictly positive with a certain bound on all these eigenvalues. And the function f is L smooth if and only if the eigenvalues of the Hessian are all bounded above by L. And this is very related to, remember that L smoothness is related to the Lipschitz constant of the gradient. And we know that the Lipschitz constant of a function is related to the largest magnitude of its derivative. So here I'm talking about the Lipschitz of the gradient. So I have to look at the largest magnitude of the derivative of the gradient, which is just the Hessian. So that is why this is something that we expect. Okay. So yes. So we often, I mean, if f is mu strongly convex and L smooth, something that you will see some people writing is that the gradient of the Hessian of f of x is less than L times identity. So this means that all the eigenvalues are less than L and is bigger than mu times identity. Okay. So this means that all the eigenvalues are bigger than mu. Okay. So so let me kind of, to finish this off, let me just conclude with two very simple examples of convex functions and try to understand whether they are mu strongly convex or L smooth. So the first function is just a quadratic function like this. So here the gradient of f of x, okay, I assume you know how to do this, so I will not do all the details. So in this case, this is just A transpose AX minus B. Okay. In fact, a 2, I think here, yeah, so 2. And so in this case, the Hessian of f at x is actually 2A transpose A. Okay, so f in this case is mu strongly convex and L smooth. So where mu is lambda min, so it's 2 lambda min of A transpose A, and L is 2 lambda max of A transpose A. Okay, so you have an idea of what the mu, the strong convexity constant is, and what the L smoothness is. Okay. Yes. Okay. So now the second example. So this function. So this is a function of one variable. So so the graph of this function. Okay. So you can see that. So when t goes to minus infinity, okay, this the exponential t will go to 0, and so this will actually go to 0. So you'll have something that's very close to 0, and then when t goes to infinity, this term, the exponential t, will dominate. But then you take the log, so log of exponential t is t. So when t is large, this function is very close to the function, just the identity function t. So this function is really something that's very small here, and then it grows, but it grows like a t. Okay, so this is just y is equal to t. Okay, so it approaches this asymptote y is equal to t. Okay, this is a convex function, but you see that this function is not going to be strongly convex. So this is not strongly convex. I mean, if you consider the domain to be the whole R, because this is approaching a linear function. Okay, and a linear function is not strongly convex. So this function has a lot of applications in what we call logistic regression, and I will show one example in this afternoon of applying the gradient method to such functions. Okay, so this has applications in what we call logistic regression. This is like least squares regression if you want, but when you have categorical variables, if you want to categorize, I mean, is this a cat or a dog or something like that? Okay, so now let me just discuss in passing some more examples of convex functions. So norms are convex functions. I already talked about this. Something that's also used in machine learning called the hinge loss. It's a very simple convex function. It's just the max of the constant function 0 and x. Okay, it has, so this is the graph. And so this is the maximum of two convex functions, so obviously it is convex. The log of the sum of exponentials, sometimes called the softmax, this is also a convex function. It's an important example of a convex function. Let's see, the largest eigenvalue of a symmetric matrix, we already saw this, how to prove that this is a convex function, because we saw that lambda max is a maximum of linear functions. And okay, something a bit, so these are more advanced examples. So if you take a matrix X that is positive definite and you look at the determinant and you take the power 1 over n. So this is essentially, if you want, this is a geometric mean of the eigenvalues of a symmetric matrix. You can show that this is a concave function, so meaning that minus f is convex. And yes, I mentioned here the sum of k largest eigenvalues. So if we've seen that the largest eigenvalue is a convex function, you can show that the sum of the two largest eigenvalues, this function which takes a symmetric matrix and outputs the sum of the two largest eigenvalues, this is also a convex function. Same for the largest three eigenvalues and so on and so forth. Again, these are not so easy examples, but they can be proved. For example, by, I mean, this last one by writing it as a maximization of over all linear function of linear functions of x. Okay, so I mean, this is just to tell you that there are certain kind of not so trivial examples of convex functions, and it is important to be able to recognize convexity of functions. Okay, and this the way you do this is kind of by practicing and by understanding what are the properties that allow you to combine together functions and that result in a convex function. For example, the pointwise maximum of convex functions and so on. Okay, so this is all I wanted to say for the preliminaries. Again, the main thing to remember is really that if you have a convex function, then it is always lower bounded by its Taylor approximation. If you're mu strongly convex, then you have a better lower bound, which is given by a quadratic function. And if you're L smooth, then you have an upper bound, quadratic upper bound on the function. And mu strongly convex and L smoothness is all summarized in the eigenvalues of the Hessian, mu being the smallest eigenvalue of the Hessian and L being the largest eigenvalue of the Hessian, of the Hessians, I should say, because you have to look at the Hessians for all possible x in the domain. Okay, so this afternoon, what I will do is that we will use these concepts to analyze the simplest possible method for optimization, the gradient method. We will discuss how, what are the convergence rates that you get for strongly convex function and for non-strongly convex functions. I will try to do the proofs of these of these convergence rates, and I will illustrate on some examples. Okay, so I guess that is it for this morning, and I will see you then this afternoon to talk about the gradient method. Okay. So I guess I will stop sharing now my iPad. Stop sharing. Okay. So okay, Abdurrahman, if you are still here, or
yes,
yes,
I
okay.
can hear you.
Yes.
Thank you.
Yeah.
So you get a lot of thanks from people, attendance. And I tried to collect some questions, but there are mainly two questions. One is very practical. People want to know how and where to get the PDF files of your presentation.
Okay.
If it is possible, of course.
Yes, so I can try to put them online. Alternatively, I have lecture notes for a course that I teach here in Cambridge that covers very similar material. So they can have a look at that in the meantime, but I can try to set up a web page and put them online. Yes.
Okay.
But otherwise, if they check my webpage, there is a yes, there are lecture notes for a course I teach in Cambridge that will cover pretty much the same material. So.
Okay. So at the end of your lectures, or maybe by now, you will send by chat for everybody of the attendants a link to your web page.
Yes, so they can check.
Some people are already asking for it.
Yes.
Okay, so this is the first question, and there was a technical question by Mr. Abdelwafi. And the question was, let me find it. In community detection, you took X non-negative and in the interval -1 + 1. And the question is now, X is non-negative or not? So, well, I don't know if you figure out what the meaning of the question.
The non-negativity is not non-negativity of the entries, but it's non-negativity of the eigenvalues, which are two different things. So in the constraint of the optimization problem, it is that all the eigenvalues of X are non-negative, but the entries, the Xij can be negative. That's fine. It's not. So it's a different concept of non-negativity.
Okay.
Yes.
Okay, so that was your response to Mr. Abdelwafi's question. Are there any other questions from the audience? Sorry, this is exactly the time chosen by the working people to run engines, noisy engines. I hope you don't hear so much of the noise.
No, I don't hear. Is it from your side? Is it?
Yes, it's some people are working close to.
Okay.
So this is, I have to tell everybody that we won't deliver certificates of attendance because it is not possible to deliver such certificates for distant attendance. Okay, and there is a question by Hussein if about using the methods you presented in portfolio optimization.
Yes, so portfolio optimization is another kind of very important application of optimization methods. That I did. Okay, I could not mention all possible applications of optimization that take a very long time, but yes, portfolio optimization in its most classical setting, that's a quadratic program where you want to trade off return and risk. So it's a quadratic program that you can solve using interior point methods, like using the CVX that I showed on Matlab. This will get you up to quite a large number of if the number of assets, I mean this n. But if you, I mean, it depends on the size of your problem, yes. But interior point methods are a good choice for such problems. And these interior point methods, we will look at them at the end of the course on Thursday. Path following methods to solve quadratic programs.
Okay, thank you. So there are questions that are still in the same vein from Fatima Al-Qasimi, how optimization is used for actuarial sciences, like for rate making purposes. So I think it's the same question, yes, the same answer.
Are they defined? And in Python, okay, I mean, obviously there are many optimization packages that you can use. Here on the examples, I used Matlab, and I used a package called CVX that you can download. It's free to use. it allows you to solve convex optimization problems. Let me put you the link. There is a version, a Python version for it, which is called CVXPy. This is for Matlab and CVXPy for Python, which this essentially allows you to write convex optimization problem in a very simple way, like you would write them on paper, and it will take care of all the all the interfacing with the solvers. So it will give, do some rewriting and so on, and give it to the solver, and then so that it's very easy to use essentially. So it's very good for prototyping and for showing demos like this and so on. Because so, and there is a version in Python, there is a version in Julia, and so on. So yes.
Any other question? Okay, so another, yes, just for, yeah, you see somebody is asking, why do you prefer Matlab?
Okay.
And there is a next question, meta-heuristic.
Okay, no, yeah, so this course, I will be dealing with algorithms where we can prove guarantees. That's an important aspect of this course, where we can prove convergence rates and say guarantees about such an algorithm. Obviously, there is a whole area of methods that are based on heuristics and meta-heuristics, things like genetic algorithms and so on and so forth, which I will not deal with in this course. But yeah, I mean, optimization is such a huge field that we cannot talk about everything, right? So,
yeah. And okay, other questions?
What about quasi-convex function? Yes, so yeah, I will not talk about quasi-convex functions, but it's a class of functions that for which we can also efficiently optimize. So it's defined by being the sublevel sets of a quasi-convex function or all convex sets. Yeah, but I will not have time to talk about it in this course.
Okay. The last question.
If we have a max convex problem. Yes, so a convex optimization problem is defined as minimizing a convex function. So if you want to maximize a convex function, that's not considered a convex optimization problem. In fact, that's in general a very hard problem. If you want to maximize a convex function, the only thing that you can say about maximizing a convex function is that the solution will be attained at the extreme points of the convex set C. But in general, these are very hard problems. So again, these are problems that for which it is very hard to give guarantees. So so I will not really again discuss them in this course.
Okay. And there is a general question, I think, that motivates most of the audience, which is related to the usefulness of the methods you presented today and you are presenting during the next days, this afternoon and the next days, regarding machine learning problems. So maybe you plan to say to present something between the link between optimization and machine learning.
Yes, so so machine learning I see machine learning as kind of, if you want, a part of statistics or whatever, but any machine learning problem, if you want to train a certain model, that's exactly what I showed in the beginning, but it was the simplest possible model where you were just looking for a linear rule between the between the predictors and the output y. And when you want to learn a linear model, then this is a convex optimization problem. You could have a linear model on a certain set of features. So you have a feature space and so on. That's still linear, so that's fine. And you can still use these methods, so like the lasso, but you can use some different methods like the SVM. These are all convex optimization problems. And the methods that we'll cover in this course will also apply for them. Now, if you talk, when you think, I mean, if you think about machine learning being just neural networks and so on, the same kind of algorithms can be applied, but the guarantees will not apply because the convex functions are not, the functions are not convex anymore. But the same algorithms and the same ideas for algorithms can still apply. So for example, tomorrow, I think I will try to cover a bit momentum, how to use momentum to accelerate convergence. And so these are techniques that are also used in that can be used in the training of neural networks. However, maybe I should mention that something I will not cover again because the field is just so wide that I will not cover stochastic optimization. So if you're minimizing a sum of very large number of functions and then you pick one at random and so on, and you take the gradient with respect to this term, this is something that I will not do. I will not cover again because there's just no time to do this.
Okay.
Okay. Good.
So there are a lot of very interesting questions regarding vector optimization. And describe some families of all families of optimization, MPC related optimization techniques, but I think we have to stop up to here for now. And then we meet you again with pleasure at 2 o'clock the Paris and Rabat time.
Okay.
In the same room, in the same Zoom room, in the same conditions, and with a live streaming on YouTube, just as this morning.
Okay.
Many thanks to you all.
Thank you.
And so see you in a couple of hours.
Yes, see you. Thank you, Abdurrahman. Thank you. Bye-bye.
Bye-bye.